Okay, so we are going to in this video work on a problem on collisions, and in this series of videos that we have been posting on techniques of dynamics analysis, we have been trying to take problems where there are certain interesting situations where the concepts of kinematics or dynamics have to be properly interpreted and applied. In this context, when it comes to collisions, we have shown interest in problems where there are infinite inertias or motions that are blocked in a certain direction. It causes such scenarios have to be dealt a little bit differently. The conservation of linear/angular momentum need to be a bit carefully formulated in those cases. So on that note, this example will look into another scenario where this infinite inertia or blocked motion in a certain direction is applicable, and through this problem we hope to show how to handle these situations. So the problem is as follows. We are considering a massless bar that is pivoted at one point. Let's say this point is O. The other end of the bar there is a particle mass, say it is M, and this endpoint is B. The bar is making an angle theta. We are not considering gravity in this case. There is another mass A, mass M denoted by A, and it is moving with a velocity V0, and it undergoes a head-on collision with this particle B. And the question is, what are the velocities of particles A and B after the collision, right after the collision, if the coefficient of restitution during this collision is E. So determine velocities of A and B after collision given the coefficient of restitution is E. So here one thing that we note that OB is rigid and massless. So we can look at this problem in a few different ways. What we'll first do is try to do a quick solution of this problem, and then we'll look into some of the details. So as you can see here, if you consider the velocities that are going to that will result after the collisions, they are like this. So you have the mass B, and you have A. So it is A is moving with a velocity v naught. It's undergoing a head-on collision. So this actually, this is the direction of the plane of contact. And this is the line of impact. Of course, these two directions are mutually perpendicular. Now, after the collision, let's say that velocity of A is VA, and let us just assume that this direction is I and this direction is J, or in other words, this is X and this is Y. I and J are the unit vectors along X and Y respectively. Now B is connected via a bar to the ground, making an angle theta. So it is quite clear that after the impact happens, B is going to have a velocity in that direction which is perpendicular to the rod, because clearly B cannot move towards or away from the rod. So if this angle is theta, then this angle is theta, so therefore this angle is 90 degrees minus theta. So VB is at an angle of 90 degrees minus theta from the horizontal, the resulting velocity. Of course, B is at rest as per the given conditions. So now in problems like this, obviously we try to apply the conservation of linear momentum, coefficient of restitution equation. In certain cases we can also apply conservation of angular momentum. In this case, and we know that in problems on collision, conservation of linear momentum can be applied along any direction. However, if we choose a direction that has a component along another direction where motion is blocked, then along the chosen direction of imposing the conservation of linear momentum, we end up getting a equation that cannot be directly used because there is motion that is blocked. So for instance, if we apply the conservation of linear momentum along the line of impact, what will happen is that because the line of impact has a component along the rod, then the infinite inertia at the pivot point will come into play, will come into the picture in the conservation of linear momentum equation. We will show it when we consider impulses. But because of the fact that you have a infinite inertia coming into the picture, what happens is that your conservation of linear momentum equation becomes unusable. It's still valid, but it's unusable. You can look at it also in this way, that if I apply the conservation of linear momentum along a direction which has a component where the motion is blocked, then the equation, linear momentum equation, conservation of linear momentum equation in that direction will not yield a usable equation. Okay? So what is the remedy to this situation? Well, the remedy to this situation is to look for a direction where the motion is not blocked and then apply the conservation of linear momentum equation along that direction, okay, by resolving all the velocities along that direction. Okay, so in this case, the direction in which there is no restriction in motion, the motion is not blocked, is the direction perpendicular to this rod. Okay, because any direction perpendicular, this direction perpendicular to the rod is not affected by this rod. Okay, so the motion is not blocked in that direction. So in other words, if I take this direction, let's call this direction A prime. This direction along VB, which is perpendicular to the rod, let's call it A prime. So we note that motion along A prime is not blocked. Therefore, conservation of linear momentum will yield usable equation. Okay, so what this means is that we need to apply the we need to basically set the initial momentum along A prime is equal to the final momentum, or the momentum right after the collision along A prime. So therefore, what is the initial momentum along A prime? Well, it is m times v naught, but we need to take this component of v naught, and so if this angle is theta, and so this angle will also be equal to let's see, this angle will be equal to this angle is going to be equal to 90 degrees minus theta, because it is just the opposite of this angle. So mv naught cosine of 90 degrees minus theta is equal to, now the velocity produced in A after collision must be along the x direction. It cannot produce any velocity along the y direction, because the impulses that will be exchanged between A and B will be along this horizontal direction. So since there are no impulses exchanged along the vertical direction, that is along the plane of contact, therefore no velocities are going to be produced along the plane of contact for A, and so the velocity of A after the collision is still going to be along the x-axis. So the momentum of A along the after the collision is going to be mva, that is along the x-axis. However, keep in mind that we are writing the conservation of linear momentum equation along A prime, so we need to take the component of that along A prime, which is going to be obtained by multiplying by cosine 90 minus theta, and B is going to exclusively move in the A prime direction, so the conservation of linear momentum then will have m times Vb. No components, because Vb is directly in the A prime direction. So cancelling out the m's and substituting sine theta for cosine 90 minus theta, we have V naught sine theta is equal to Va sine theta plus Vb. Our goal is to find Va and Vb, and so we have one equation. Now the next equation is obviously the coefficient of restitution equation. Now we when we apply the coefficient of restitution, keep in mind that the concept is that the coefficient of restitution is essentially very local behavior that affects the relative velocities before and after the collision, and it is an instantaneous, it is because of the instantaneous compression and the restitution of the two surfaces that are coming in contact, and the coefficient of restitution is therefore exclusively always written about the line of impact. Okay, because the deformations and the restitution of the surfaces that are coming into contact happen directly along the axis of impulses, and the axis of impulse in this head-on collision is going to be in this line of impact. So the coefficient of restitution equation must be written along the line of impact. So coefficient of restitution equation written along the line of impact. And so since that's the case, we are going to write E is equal to the relative velocity of departure divided by the relative velocity of approach along the line of impact. So what is the relative velocity of approach? Well, A is approaching B with a velocity of v0 along the line of impact. So it is v0 minus 0. What is the relative velocity of departure? Well, as we have seen before in other examples, if you are writing the relative velocity of approach to be the velocity of A minus velocity of B, then the safe way to write the relative velocity of departure is to write the velocity of B minus velocity of A. This ensures that we do not have to take the squares of the two relative velocities in formulating our coefficient of restitution equation, because the coefficient of restitution is a positive term. So we need to, if we don't take squares, we have to ensure that the right hand side is positive. And to make the right hand side positive, one way to do that is, without taking the squares, is to make sure that if we are doing A minus B in the denominator, then we do B minus A in the numerator. So what is the velocity of B along the line of impact after the collision? Well, it is VB cosine 90 degrees minus theta. And what is the velocity of A after collision along the line of impact? Well, it is VA. So therefore we have EV0 is equal to, and substituting sine theta for cosine 90 minus theta, we have VB sine theta minus VA. So now we essentially have two equations and two unknowns, so we should be able to solve for the velocities of A and B. So let us carry out the solution. From 1 and 2 we have, let's see, if we multiply equation 2 by sine theta and add it to equation 1, then what we are going to get is VA sine theta in equation 1 will cancel with minus VA sine theta in equation 2. So we will have VB left. So we'll have V0 sine theta plus EV0 sine theta is equal to VB plus VB sine squared theta, because what we have done is, so this is obtained by multiplying 2 by sine theta and adding to 1. So from here we get then that VB is equal to V0 sine theta 1 plus E divided by 1 plus sine squared theta. So that's our solution for VB. And then from 2 we get the expression for VA. So VA is equal to E, well, it is VB sine theta minus EV naught, right? So it is V naught sine squared theta 1 plus E divided by 1 plus sine squared theta minus EV naught, which can be simplified, and we will have, let's see, we will have V naught sine squared theta, EV naught sine squared theta, and minus EV naught and EV naught sine squared theta. So EV naught sine squared theta is going to cancel, and so we will have V naught sine squared theta minus E. So V naught times sine squared theta minus E divided by 1 plus sine squared theta. So let's just quickly check if this is good. V naught sine squared theta and EV naught sine squared theta. EV naught sine squared theta will get cancelled. We'll have this guy and we'll have V naught. Yeah, this is good. So that's the velocity of particle A. So that's our solution to this problem. Now let us look into this a little bit more from the perspective of the impulses that are produced at the time of collision. That's going to give us a little more insight into the inner workings of the different forces and hence the type of velocities produced due to the collision. So if we consider the impulses, so if we, let's draw the two particles at the instant of collision, what's going to happen is A is going to impart an impulse F delta t, and B is going to then impart F delta t in the opposite direction. Now B is connected to the ground by a rod. Well, let us separate out okay, so I have just erased this part which showed the pivot and put it separately. This is the point O, this is B, and this is A. Now at the instant of the collision, another thing that is going to happen is that there is going to be an impulse that the ground will provide. It's called that F bar delta t, and that will be in response to the same F bar delta t that is provided by the particle B through the bar to the point O. Now this is all happening together because the rod is rigidly connected, and it is a rigid rod. It is connected to the point B, so when the collision happens, the rod also feels and it transmits an impulse along its length. So there is an impulse that goes to the ground, and the ground provides an impulse, and those impulses are given by F bar delta t. And of course this angle is theta. And so after the collision, we are saying that there is a velocity VA produced and there is a velocity VB produced. VB is perpendicular to the rod, and this is our line of impact. Right, so if I write the equation, the linear impulse momentum equation, so the linear impulse momentum equation for A, and again we are going to consider this as our x direction, this as the y direction with the unit vector j. Then we have, and A was moving with a velocity v0, so we have mva minus mv0, so that change in linear momentum is equal to the impulse, so it is negative f delta t. Right, because f delta t here is in the negative x direction, and we are expressing all these momenta in the positive x direction. So the change in momentum in the positive x direction is given by the negative delta f delta t. So that's equation 1. Now if we take the linear impulse momentum equation for B, then what we have, let's say we are writing about this direction, so we have initial momentum is 0, about B the final momentum is mvb, cosine of 90 degrees minus theta, because keep in mind that this angle is 90 degrees minus theta. So that is equal to the f delta t. However, there is also a f bar delta t. So there is a f bar delta t, and so the momentum that f bar delta t, or rather the impulse that f bar delta t provides along the line of impact is minus f bar delta t. If this is 90 degrees minus theta, then this is theta, so cosine theta. Okay, so that's the linear impulse momentum equation along the line of impact. And we see that if we eliminate f delta t from equations 1 and 2, then we are still left with f bar delta t, and that is going to be problematic because we don't know what is f bar delta t. And the reason we'll not be able to find out what f bar delta t is because it's an impulse that goes to the earth, and which is considered to be infinite inertia in this problem. And so because there are infinite inertia, even if we write the conservation of linear momentum equation, we won't be able to make use of it. It's not going to be an usable equation, right? Now we can write the linear impulse momentum equation. This is along line of impact. Right, we can write the linear impulse momentum equation for B, let's say along this direction A prime. We have identified this direction as A prime. So if we apply the conservation of linear momentum equation, or the linear impulse momentum equation on B along A prime, then what happens is, so linear impulse momentum equation of B along A prime. If we do that, then what we get is the following. We get the initial impulse is initial momentum is 0, the final momentum is mvb, right? That is along AA prime, and that must be caused by the effect of these two impulses. So what is the impulse along AA prime for f del t? Well, it is f del t cosine of 90 degrees minus theta. Now let's look at the effect of f bar delta t. Now we note that f bar delta t, by virtue of being perpendicular to the AA prime direction, does not have any component along AA prime. So this equation 3 does not have an f bar delta t, unlike equation 2, which was along the line of impact. Okay, now this gives us an opportunity, because if I now consider equations 1 and 3, I can eliminate f delta t and come up with an equation which does not contain these impulses, but rather only contain the momentum expressions for the different particles. And that is essentially going to be our conservation of momentum equation, which is usable, because again it is using finite inertia and not the infinite inertia of the earth or the blockage in the motion. So therefore what we can do is, therefore from 1 and 3, if we multiply 1 by cosine 90 minus theta and add to 3, what we are going to get is cancellation of this f delta t term, and we'll have mvb is equal to mva, or rather mvb plus mva cosine 90 degrees minus theta minus mv naught cosine 90 degrees minus theta is equal to 0. And so if I cancel out m from all the terms and replace cosine 90 degrees minus theta by sine theta, we have got vb plus va sine theta is equal to v naught sine theta. And let's see if this matches with our linear momentum equation that we had derived earlier. So note that our linear momentum equation that we had derived earlier, if I call this equation 4, matches with linear momentum conservation equation along AA prime. You see, in the previous page we had derived this equation, the conservation of linear momentum along AA prime, which was VB plus VA sine theta equals V naught sine theta, and we get that same expression, VB plus VA sine theta equals V naught sine theta. So this again shows that if we resolve everything using or if we incorporate the impulses and we write the impulse momentum equations and try to eliminate the impulse, the intermediate force, short-lived force that is causing the changes in momentum, then we get the linear momentum conservation equation in the appropriate direction. Okay, we can skip this step with the understanding that linear momentum equation will give us, linear momentum conservation equation will be usable only when it is applied along a direction where there is no blockage in motion. But this is one way to go back to the basics and implement the impulses and derive and show that that is indeed the case. Now there is another thing that we can do in terms of our analysis, and that is apply angular momentum conservation. And the reason we can apply angular momentum conservation in this scenario is that let's go back to this figure. The reason we can apply the conservation of angular momentum is that if we take the conservation of angular momentum about the point O, then we see that f delta t over here, they will produce equal and opposite cancelling angular impulses. All right. Similarly, f bar delta t, not similarly, but F bar delta t will not produce any angular momentum about the point O, because F bar delta t directly passes through the point O. So if we take the angular momentum of this system about the point O, we note that the angular momentum is conserved. Okay, as I said, it is because F bar delta t goes through O, so it produces no angular impulse, and the F delta t, they are producing angular impulses, but they're equal and opposite, so they cancel for the overall system. So therefore, angular momentum conservation can be applied about O. And if we apply this angular momentum conservation, what we get is, let's see what is the initial angular momentum. A is moving with a velocity v0. So if we say that this is I, j, and k is pointed upwards, so then, all the angular momentum are going to be perpendicular to this page, so they'll be either in the positive z direction or negative z direction. We are going to represent angular momentum in the positive z direction as positive and negative z direction as negative. So mv0 is producing a negative angular momentum initially. So you have mv0, and the perpendicular distance from the point O is going to be, let's say that the length is L. So L cosine theta, L sine theta is the perpendicular distance, right? So that's the with a negative sign, because mv0 is going in this direction, so it's producing angular momentum in this direction, which is into the page, and z is positive going out of the page, so this is a negative angular momentum. And what is the angular momentum of A after the collision? It is mva, negative mva L sine theta, right? Because we assume that A is moving towards the right after the collision. So if it is moving towards the right, it has a momentum of mva in the positive direction, and the arm length is L sine theta. So it is producing angular momentum which is going into the page, so a negative sign. On the left hand side we have the angular momentum before collision, right hand side we have the angular momentum after collision. And we will have VB. So VB is perpendicular to L, so mVBL is going to be the angular momentum, and it is again producing a clockwise angular momentum, so it's going to be negative because we are considering counterclockwise, which are pointing outwards, to be positive. So if we now cancel ML from both sides, what we get is V0 sine theta, which is equal to VA sine theta plus VB, and this is again same as equation 4 above, right? We get the same equation as the one obtained from conservation of linear momentum by applying conservation of angular momentum, right? So you could proceed by applying the conservation of angular momentum about the point O, the fixed point O. Remember that for a system of particles, the conservation of angular momentum can be applied either about the center of mass of the system of particles or about a fixed point. So in this case, the fixed point seems to be quite reasonable because of the fact that if I take the angular momentum of the fixed point, then we don't have to worry about F bar delta t, and plus it's a fixed point, it's a legitimate point about which we can write. So that's basically this problem. We have looked at, we have derived the solution, we have looked at why the linear momentum conservation equation is valid about AA prime by resolving the impulses and writing the linear impulse momentum equations, and we have also shown that the linear momentum conservation equation coincides with the angular momentum conservation equation about the point O. So that's it for this video. Thank you.